Hey, John here. Let's look at the linear search, or sometimes called linear probe, okay? Now, what this is for is to find things. You want to figure out where, let's say we're searching for the element in this array here whose value is 8. All right, now linear probes can be applied to linked lists and other data structures as well, but right now we're going to just focus on how we would write an algorithm to find something in an array, okay? So what we really want to do is find the element whose value is 8. And we can see clearly it's right here. That would be 0, 1, 2, 3. So the index number of the element containing an 8 is a 3. So what we need to do is write an algorithm here that'll always figure out where the thing is, return the index number of what we're looking for. Okay, so let's use two variables. We've got our array that's filled with the values we want to search, okay? We have the number of elements in the array. That'll be the black pen. And in this case, it's obviously 6. And I like to think of the number of elements in the array as the index number of the first element that does not actually exist, or that does not have a value, all right? So element number 6 would be here if there was one, all right? The blue pen will represent a counter. We start the counter at 0, and we ask, is the current value of the counter less than the number of elements in the array? Yes, it is. Therefore, we can proceed to ask, is the element value at index 0 equal to the one we want? No, we're looking for 8. What do? We add 1 to the counter. Then we ask, is the counter less than the total number? Yes, it still is. Does the value of the element in the array at the current index number equal what we want? No. Go to the next one. Is it still yes? Yes. Is that value the one we're looking for? No. Add 1. Is it still yes? Yes. Is that value the one we're looking for? Yes, it is. We now return the value 3 because the counter will be equal to 3. All right. It is really as simple as this. Now, what happens if we were searching for something like the number 3 instead of the number 8, right? Well, we would not have found it yet, so then we would continue adding, and we'd still say, yes, it's still less than the number of elements. Is that the one we're looking for? No, add 1. Are we still less than the total number of elements? Yes. Is that the one you're looking for? No, add 1. Now it gets interesting, okay? Is this still less than the number of elements? And the answer is no. We need to decide at this point on a sensible value to return that represents the I didn't find it situation, okay? We call this a sentinel value, and we have to pick a value to return from our subroutine that says it's not there. Well, could we return some value, maybe like a giant number? Well, in theory, yes, but then this code would fail someday when we have more and more memory and more elements. It's just a terrible choice, bad idea. It won't work forever. What will guaranteed work for all eternity and never fail? -1 would be a good sentinel value, okay? So if we return an index that literally can never be something way over here, that's a great choice. So this is rock solid at this point. If you find it, return the index number. If you don't find it, return a -1, okay? Let's look at some code. Okay, first things first, thank you to Sergey. If you look through some comments in my how to write things to standard out video, I use this expression rather sloppily in that code. Also, Giovanni, who also commented in the same video of another problem caused by the way I was being sloppy about this. So let's quickly look and see what's going on here. Sizeof is a compile time operator. It literally is an operator. This is not a function. This is not a subroutine. It doesn't execute at runtime or anything, okay? This is just a really weird looking operator. So this thing represents the size of A represented in bytes. So as far as the compiler goes, when your code is compiled, this looks a lot like a numeric constant value, okay? As does this. It turns out that an int in this particular machine is 32 bits, which is 4 bytes. So size of A will be 4,000, all right? Size of A0 is 4, because it's the size of this int here. Therefore, 4,000 divided by 4 is 1,000. This essentially sets n equal to the number of elements in A. This only works if you define A like I've done here with an actual size here, with an actual number at compile time. If you leave the square brackets empty or something like that, then this won't work, okay? Because the compiler doesn't know the size of A is my point, okay? Turns out that dividing a numeric constant by a numeric constant will result in the compiler doing the division during compilation and give you a numeric constant value. Okay, so it doesn't actually have to reevaluate this thing while it's running. However, having this all over your code is just sloppy. And what if somebody changes it subtly? Somebody's looking at your code. This is just what I gave you was just terrible practice. You know, do as I say, not as I do. Sorry about that. Anyway, so what is the data type of this thing? Well, it turns out the size of operator, it depends on your compiler and your operating system. But they give you a data type called size t. This is the type of the size of something, whatever that is. It turns out it's an unsigned integer, which brings us to Giovanni's point, who also commented in my same video for compiler warnings that you get if you run the code exactly as I've given you. The size t on this machine turns out to be a 64-bit unsigned integer, okay? If you ever compare a size t to an integer, like I want to down here. If this was an integer, or just a numeric constant in here, because if I just type 1, 2, 3 in there, the compiler will treat that as an integer, which is assigned, in this case, assigned 32-bit number. And you would try to compare the magnitude to a size t, which is what you would get if you just put this in there. Okay, you get a warning that says, I don't like to do that. Okay, so that's another sloppy thing. So let's look and see what's going on here. I've got an I and I've got an N. They are both of type size t, which is the correct value for anything of this type. All right, so far so good. I got a thing called N. I got a thing called I. When you're looking at this as a programmer, these look like variables. This one, however, is not a variable. This is a constant expression, which is not a variable. Not only is it constant, the whole expression is constant, all right? This thing here means that the compiler needs to do all the math over here, create a value that's invariant no matter what. If I merely declare it as const without the expr, I'm creating something that's very different, and we'll talk about that in some other video, all right? The short of it is that if you just say const over here, you're not creating an invariant during compilation. You're creating something that is invariant during execution. And the subtle difference is that n is a real variable that can take, in any way, depending on how well the compiler would optimize your code, it can consume memory. It may not be able to optimize it as well as if I guarantee that it is immutable, period. Okay, this is a better way to do this if this really is an absolute fixed value. Okay. So what do we got going on here? Well, I is less than n. In other words, while I haven't overflowed my array yet, go get something from standard in and store it in my array. So this thing prevents us from overrunning the array and corrupting memory. Subtle side note, don't put I++ in this while loop in this expression here, because when you read the last value, or well, shall I say one past the last value, this will fail. Okay, this will return a failed status, which is going to end my while loop. And when that happens, it will increment I. And when you get down here, I will be too big. It'll be one more than it's supposed to be. So you need to put the ++ I in this while loop. All right, so a bunch of side notes. This video is getting too long. Anyway, that's the short of all this stuff here, okay? Anyway, so I wrote a little program, a little subroutine, all right, up here called look for, all right? And the only reason I wrote this, we call this a wrapper function. What is it going to do? It's going to print out the value we're looking for, and we're going to make sure it's 5 spaces so that the output looks nice. It's not all staggered all over the screen, making it harder to read. Then it'll put a colon, and then it'll print the return value that we get from our linear probe function up here, okay? And we're going to just pass these same values into the probe function that we got from into the wrapper function. So what does this do? It does exactly what we just saw. It says, look, for I equals 0, while I is less than n, which is the number of elements in our array here that we want to scan through, okay? And then add 1 to I every time through the loop. So we ask if the current element, a sub I, is the value I'm looking for. I'm going to return the index number I. Simple as that. If it never finds it, eventually I will go all the way up to this value n, It will not have been located in our array. We return a sentinel value -1, okay? Notice again I made I a size t in here. If I did not do that, if I made I an int here, what it would do is it would be comparing this integer variable to a size t, and the compiler could warn you in here because it's doing a comparison that it might not be able to do. All right, so let's go ahead and run this thing. Now, I've created a test file here. Let's look and see what's in the test file. There's a bunch of numbers in here. I just put one per line to make it easy for myself. Let's review real quick what we're looking for, right? We got a 68, a 9999, a 22, and a 4. I happen to know this is not in my array. Okay, it's not in my input data. I've chosen some test values that are what I would consider to be the corner cases, right? What's 22 and 4? Well, 22 is the very last element in the array. You'd be a fool not to check to make sure that your loop didn't end early. I mean, this is kind of hard to screw this up, but you'd be impressed at your own incompetence, as I am, even in the case while I'm just trying to divide two numbers down there in my other video, right? So 4 is the very first element in our array, all right? So these are kind of special cases. Did I start where I'm supposed to start? Did I actually check all of them, including the very last one? And can I find those? What else am I searching for? I'm looking for a 68 and 4 9s. Well, it turns out 68's in here somewhere. I know that. In fact, we can run it and it'll find it for us. Where is 68? It's in here. It's right here. It's the second to last one. And 4 9s, if you scram through here, are not in there at all. So these are basically the 4 cases that I think are worthy of checking. So let's run our program. And we will read in the test data instead of typing it all in and wasting our time over that repeatedly, okay? So what are we going to do? 68 was fine in element number 24. 4 9s was not found at all. We get -1. 22 was found at position 25, and the 4 was at position 0. 4 is the first element. That makes sense. 22 is the last element in our file. Well, we could sit here and count all of these if we want to. You could open it up in a text editor, scroll to the bottom line and ask what line number am I on, or I can just ask the system to count them for myself. It has 26 total lines in it, okay? So let's run it again. 25 is where it found the last one. How come this is different? It's different because the first one is 0. 0 through 25, these are the indice numbers, 0 through 25. 26 is the n when we've read them all in. That's the total number of them, right? So if this is, what, 25, then this must be 24, so all those test cases all work out. So that is a linear probe. Let's look at something that we can do if we make some assumptions, right? What if this array is sorted instead of unsorted? See our test.dat file? This clearly is not sorted, okay? We can sort it and do another test here. Let's say sort. In Unix, there's a sort -n means these are numbers, they're not names. Otherwise, it would do a dictionary style sort. We can read in our file, test.dat, and we can write out another file called test.sort, like so. We then check it because we never underestimate our own incompetence, and we make sure that it is sorted. Look at that. Okay, it's sorted now. Clearly, the big number's on the bottom, the little number's on top. We can run our linear search program another time now. We can still see that. Oops. This is an example on how not to test your program. After you've sorted your file, you want to run it with a sorted file. Okay, I found it's possible that these numbers would be the same as they were before, but very unlikely, okay? So after we sort the file, the value 4 is still at element number 0, simply because that was the lowest one to begin with, right? So here's the value, the data file before we sorted. So both of them are still the first one. These other values have changed. Clearly, that's still not in the file, all right? But number 22 is in location 4, and 68 is in location 6. 0, 1, 2, 3, 4, 5, 6 for 68, and 4 for 22, right? So still works. That's all fine and dandy. Now, why did I sort this? What am I going on about here? Well, look at this. If you know, if and only if you know for an absolute fact that your input data is already sorted, we can put an optimization in here, can't we? I'm going to put this in like this because I want to make sure that we have it's in our face that we know that this is special code, right? This makes it easy for me to comment this code back out, right? If I change this to an if 0, this tells the compiler not to compile what's in between this and this, okay? If I type if 1, that's if true. The compiler is the thing that's actually interpreting these commands here, all right? What are we going to do? If we know it's sorted, we can say if the value of the element that we're currently looking at is already bigger than what we're looking for, then we know for a fact it is not going to ever be found. Okay, now this could be really useful. What if there's 100 million elements in that list, in this array up here? And what if we're searching for like 72? And all of a sudden, in the data file, we're running along and we reach this. Do we really need to look down here? No. If it's sorted, we can end early right there. So here's an optimization that's useful if and only if your data is already sorted. And as you can see, we got the same results, right? Now let's look and see what happens if it's not sorted, all right? I mean, you should be able to foresee what's going to happen here, right? If your data is not sorted, you do not want to make this optimization. It just doesn't make any freaking sense. So let's take a quick look at test.dat again. Why did all these show up as -1s? Why? Because as soon as I got to 92, it said, well, it can't be down here because all these values down here are supposed to be bigger than 92. And of course they're not, because this is the data file that's not sorted. Okay, that's why I made a big stink and made this like this. If and only if you know your array is sorted, you can start making these kind of optimizations. All right. Obviously, if I turn that back off, it'll start working again. Okay, so what do we know about this? What is the time complexity of this problem? We call this order n, big O n. This is order, n. Why? Because on average, let's say you probably, if this data is purely random, and the things you're searching for is purely random, and you do run this many, many millions of times, on average, you'd probably wind through half of this array, on average. So you'd say, on average, there's be n over 2 comparisons in the linear probe search, right? And when we talked about big O notation and orders of complexity, we know we throw away constants, therefore that's left with n. This is order n time, we call that, okay? So there's all you ever wanted to know about linear probe and a side note of data types. Thanks for watching. See you next time.